Hi, everybody. I decided to skip the very last section in chapter four, and we'll start today on uh, chapter five about solving congruences. And the reason is really the content of that last section was one just small thing. To be honest, they did some work about showing what are the final digits of numbers that are cubes, and it turns out you can show that every number appears as the final digit of a cube. And that's when you talk about final digits of numbers in base 10 arithmetic, you're really talking about um, modular arithmetic to the base 10. So that whole little problem was introduced mostly as a way um, to give this piece of terminology congruences, or here in bigger writing, congruences. I don't know how this word is supposed to be pronounced. I got to be honest here. I've always said congruences with the emphasis on the first syllable, but there are people who say congruences. So congruences. I don't know. We're going to try to solve them anyway. The sort of easiest kind of thing to look at is what's written right there. A times x is congruent to b mod n. That actually looks terrible when I try to highlight it, so I'll unhighlight it. But you know where I was pointing. Now, what does that say? Maybe not clear, but a, b, and n would be fixed numbers. And then, so given those values, can we find an x that makes this whole thing true? So while everything's a letter here, think of a, b, and n as constants, variables that are not in fact changing. And then x is a true variable where we're seeking its value. And okay, so there's a proposition here which says that congruence, ax congruent to b mod n, has a solution precisely when the GCD of a and n is a divisor of b. So you look at the thing that's a multiplier on x and the modulus that you're using n, find their GCD, and if that divides into b, you'll have a solution. That's what it says. So here's a good thing to look at and just test ourselves. Which of these have a solution and which ones don't? So in the first two, the n is 15. And the coefficient of x is 7 in this first one and 6 in the latter one. Now, 7 and 15 do not have a common divisor, or if you like, their common divisor is 1. Their GCD is 1. And does 1 divide into 8? Yeah. So according to that proposition up above, this means this should have a solution. I'm not spotting one right off, but I believe it has a solution. Now let's look at the next one. 6x congruent to 8 mod 15. Here the coefficient of x and the modulus 15 do have a GCD. A non-trivial one, right? Their GCD is 3. And does 3 divide into 8? No, it doesn't. So that one should have no solutions according to the proposition. Here we have 7 and 14 are the numbers, and those clearly have a GCD of 7. Does 7 divide into 8? Nope, so no solutions. 6 and 14, they do have a GCD. I think it's just 2, though. They're both even. But 2 divides into 8, so this last one should have solutions. No, well, now let's look at the proof of this proposition because it's instructive what they do. I just clicked the proof and nothing happened. What? Oh, there we go. So, okay, they say the proof is straightforward as long as we know the stuff we just did about Diophantine integer equations having solutions. So, I always joke with students in the Intro to Proof course that if somebody uses the word clearly in a proof, you should concentrate on that spot because that's probably where they've made a mistake. I do think that this, in fact, is actually all these connections are indeed clear, but I always find it humorous then when in real life I encounter the word clearly and it's actually right, used correctly. Anyway, so the first one is just saying, look, you have a solution x to the ax congruent to b mod n. So the sort of the thing we're interested in. That's equivalent to saying there's a solution x to n being a divisor of ax minus b. What? Why? Well, that's actually the definition of this congruence symbol, right? You put the congruence symbol there if the difference between the two things is divisible by n. I often think of it as they have the same remainder mod n, but that means if you subtract them, you take away those two remainders, those two equal remainders, and you get 0 as a remainder, meaning n divides evenly into that difference. Okay, so if there are solutions x to n being a divisor of ax minus b, how does that get us this next line? It's just introducing a new variable, y, and if n goes into ax minus b, that means that ax minus b equals n times something. Y is the something. So if you know that n divides this difference, then n times something will give you that difference. And this last thing is just rearrangement. Just add b to both sides, subtract ny from both sides. But that puts it in the form of a solution to a linear Diophantine equation. Then it says, well, as we know from theorem 3.1.2, the final equation, this last one, has solutions precisely when the GCD divides b. In other words, the thing we were after. So I hope that's seemed familiar when we looked at the GCD of the two numbers and so on. So this is good. I want to show us I'll show you an alternate approach to thinking about solutions to these linear congruences. But let's follow through with the next little piece here. It says, if you can construct one solution to the congruence, then you can construct all of them. And generally there will be multiple solutions. In fact, you know exactly how many there are. I find it disappointing that he didn't tell us how many there are, because it's an easy enough thing to see, but it's included in the proof. With one small typo we've got to look at. So you basically think about the proof of proposition from the previous chapter. Well, the proposition, how do I say this properly? The proposition we just looked at with the result from the previous chapter. You don't really care about the why, other than it exists. It's the thing that tells you that the divisibility thing works out. So, well, suppose you have one solution. That's the same as having a solution x naught y naught to this equation. Fine. We've got a theorem from chapter 3 that tells us what those things look like. They look like this. They look like x naught plus n over d times a constant. And the k is just any integer. In fact, in the setting of finding solutions to Diophantine equations, or equivalently finding lattice points that lie on a particular line, k could be any integer. But if we're going to reduce everything mod n, k can't just be anything. It's a value between 0 and n. So what happens, and here's where the typo is, he wrote t rather than k right there. But you just let t go from 0 to d minus 1. Let k go from 0 to d minus 1. In other words, there are d solutions. All right, so I think an example might help. Here's an equation where, do you see what the GCD of the coefficient of x, 12, and the modulus, 21, is? looks like 3. Right? So you're going to have 3 solutions. And the gap between those solutions is n over d, which is 7. You got to, if you get us an initial solution, then you can find the rest of them by adding n over d multiple times. But, all right. So what he does first here, and this is a fine approach at first, but later we'll see how to do this accurately, is just poke around until you find a solution. There's, there are going to be some, and they're not all that rare. They're only they're separated by n over d. So before you go 7 units, you should be able to find one. So that's what he's doing. He's just multiplying 12 by 1, then by 2, then by 3. And as soon as you get to 3, you've found one. 36 is 21 plus 15. So yeah, 15 is our number there. So you can take 3 to be the original solution, or the generating solution. And then if you add 7 to that, you'll get another one. And then 7 to that, and you'll get yet another one. I don't know why he indicated this one with a minus 4. 3 works. 3 plus 7 is 10. 10 plus 7 is 17. 17 mod 21, you're almost up to 21. So think about backing down from 21 to 17. You have to go 4 units in reverse, right? So that's why minus 4 is there. So you can actually state what the general solution is. 3 plus 7k. I don't think I would say this, though. Not that k is an integer, but rather that k is 0, 1, or 2, really. It's a number that works as a mod 3 remainder. Okay, so let me do the alternate approach to this stuff, which I think is more visual, and I think it's kind of an interesting thing to spot and see the connection. And this is about drawing stars. So let's start by, I'm going to create a polygon that has quite a few edges on it. So I think I want it to be about 15 to begin with. And the only reason that's there is to get me 15 evenly spaced points around a circle. I'm going to draw a little circle at the top there. That's 0. Okay. And then we're going to draw stars on this diagram. Has everybody done the thing where you learn how to draw a 5-pointed star by doing like that? Coming back. Well, now we're going to try that with things other than 5 points. So we've got these 15 evenly spaced points. I'm going to draw a polygonal line thing here. Let's make it a nice color, though. How about blue? I guess. And also I'm going to draw it with a fairly thick pen. All right. And I'm going to pick more or less a random number of sort of spaces to skip over. How about we skip 3 spaces? I'll draw a star by going 1, 2, 3. Land a point there. 1, 2, 3. Land a point there. 1, 2, 3. There's a point. 1, 2, 3. Kind of. Oh yeah, look at that. It just ends. So the star I created isn't much of a star. It's a pentagon. Fine. What if let's change colors and draw and pick a different skip amount. See, these points on a circular thing here can be thought of as the mod values, the things that go in square braces. 0 through 14 are the representatives for those mod classes, those congruence classes, mod 15. And what we did by skipping over 3s is actually multiply by 3 over and over again. That is, this is 1 times 3. This is 2 times 3. This is 3 times 3. 4 times 3. 5 times 3 is 0. And it is in mod 15. How about if we skipped over 5 this time? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Not really a star, a triangle. Um, you know what? Here's a good one. Let's make it red. How about if I skip from here to there, which could be thought of as skipping 2 units on the blue polygon, or it can be thought of as skipping 6 units on the original Mod 15 clock system I was trying to set up. This is the first one that actually gets us a star. Excuse me. And it turns out those are the stars that you get. Those are all of them if you're on a Mod 15 clock. You either have threefold symmetry, and when you have threefold symmetry, a triangle is the only way to make a quote-unquote star here. Or if you have fivefold symmetry, then you get 2 options. You could have the outer thing that looks like a pentagon, or the inner thing that looks like a star. What's the connection between them? Notice that, remember the number was 15 for the number of sides for the modulus that we're working at. And the 2 things that created fivefold symmetry type stars, they all visit the same points, by the way. It's 0, 3, 6, 9, 12, and back to 0. So both the blue and the red have solutions when the numbers are in the set that I just named. It's 0, 3, 6, 9, 12. The connection between them is the GCD of how many we skipped. In other words, the number we're multiplying by, and how many positions there are on this clock. So GCD of 3 and 15 was 3. 15 over 3 gets us 5, which is how many points there are on the star. Or if I look at the green thing, we skipped over 1, 2, 3, 4, 5. The GCD of 5 and 15 is 5. And 15 over 5 is 3. And see how you get 3 points on that thing. So, well, let's delete all this junk and start with a different modulus. I'll leave that thing to mark the top of it for me. That's cool. How about if we got it to 21? Not 200. Yikes. 21. All right. I am going to try to draw a careful star. Oh, no. I didn't want it to be red and fat. Let me fix that. We'll put it back to black and thin lines for that outer thing. But when I get to drawing stars, I want them to be in a nice color. What haven't we used yet? How about purple? And let's make it more vibrant by fattening up the line a bit. All right, so I have, what was the modulus? I just wrote it down and I forgot already. 21, wasn't it? Okay. Let's pick something that does not share any divisors with 21. 21 is 3 times 7, so anything that doesn't have a 3 doesn't have a 7. 5? So let's look at what a skipping over 5 things at a time does for us. 1, 2, 3, 4, 5 to here. 1, 2, 3, 4, 5 to there. Well, look at that. We almost landed diametrically across where we started. 1, 2, 3, 4, 5 to there. 2, 3, 4, 5 to there. We almost landed back where we started. It was interesting. That makes this is actually kind of nice in terms of being able to draw it a little more quickly. I don't have to keep counting to 5 because from here I'm going to go one before wherever I got from the original circle. Yeah, so there's where it should go. And then to here, here. And that's going to kind of keep going. You see the pattern we're getting? It looks like what you'd get if you look at video feedback. When you point a camera at its own monitor. Oh, almost ended it prematurely. Nope. There's one more set of things to fill in. Wow, isn't that cool? It's an interesting design. It looks like a little bit like Spirograph if you've ever played with that toy. Well, this is different. This is a very different situation than what we had before because this star has as many points as there were on the clock. We've got a situation where the multiplier 5 is relatively prime to the clock size 21, which means that any number, well, it means the GCD will be 1, so 1 will divide any number. That is, regardless of what b is, ax congruent to b mod 21, or I'm sorry, I shouldn't say ax, 5x congruent to b mod 21 has a solution for every b. It has to do with the stars ending up having points at every position on the clock. But well, that's nice, but that's not the general setting. The general setting is you might have some common divisor with the clock size. Maybe how about 9? 9 is, I think the only factor it shares with 21 is 3. So let me just delete this beautiful purple star and we'll draw another beautiful purple star. What does it look like if I start at 0 and go 9 units? I think straight across from the 0 up there would be in between these two spots in here. And this is 21 as the full size of the clock, so that position would be 10. So here's where 9 is. I guess there's no way to do this, but go ahead and count. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 to there. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, 6. Oh, come back to there. Now we got a star. Truly looks like a star. Actually, isn't this the symbol they use in the Game of Thrones show for like the big religion? Yeah, the 7-pointed star. It's a big thing on that show. Anyway, what my takeaway is there's spots on the clock that aren't on the points of these stars. There's positions like 1 and 2, which are never going to be multiples of 9. The points of the star are the things that are multiples of 9. So again, what was the GCD? 3. And 21 over 3 is 7. That's why we got a 7-pointed star. We were skipping over 3's, which means we were thinking about multiplying by 3. The coefficient of x would be 3. And, well, that's kind of cool. There's, I think there are 2 other sorts of stars that are 7-pointed. Let me show you them. Let's see, we have magenta, so I should go with yellow and what's the last one? Magenta, cyan. I don't see if, yeah, that one's cyan. Let's do cyan first. If you just skip over by 3's, I mean, at some level, this is only technically a star because it's really a polygon, isn't it? You get that thing, and changing to yellow, we would skip by 6s. So there are 3 different kinds of 7-pointed stars. All of them have the same feature, though. They all land on these 7 points, or mod 21. 0, 3, 6, 9, 12, 15, 18, back to 0. Yeah. So certain congruences will not have solutions. Others will have many solutions. That's sort of intriguing. And the thing that determines both issues is the GCD. If the GCD is 1, all things have solutions. I think then these solutions end up being unique. I'm not sure. I'm not sure if I'm speaking correctly there. I feel like the number of solutions should be then. No, sorry, had to go through a little group theory thinking in my back of my head there. The solutions will be unique in that case. And if the GCD is something bigger than 1, then you have certain right-hand sides that you'll never be able to get to. So, and then, the solutions happen with multiplicity in that case. It does feel interesting, like there's some kind of a conservation going on. We have fewer things that have solutions, but there are more of them. So maybe you get a total that's always fixed. I'm not sure. All right, so that's that for sort of showing you a arts kind of a geometric way of thinking about the same issues. I'm going to leave the screencast for now, and we'll do some stuff on the board. I know I said I was going to go out to the whiteboard, and I'm not right now because I realized I forgot something, which is I wanted you to see a special situation that happens when the clock size is a prime number. Because it's a little bit interesting, I think. How about if we make a clock with 11 points on it? Not 116. There we go. That should be good. Well, of course, I would like to sort of look at multiplying by all possible numbers. So multiplying times 1 times x equals something. Well, that's just going to correspond to jumping around the clock by moving one spoke at a time, or one segment at a time. In other words, you'll draw this outer perimeter of the clock. So the smallest thing that really makes sense to try to draw a star with is when the skip amount is 2. Oh. So let's do that. Skip 2. Skip 2. 2. 2. Oh, I thought I was going to come back to the beginning, but I don't. Nope, we have to go around a second time. Maybe we'll have to go around a third time. Nope, we just ended. And the star I got there, that's rather pleasing looking, I think, but it's, well, the thing to notice is that it's got a spike or a tip on every single position around the clock. Why did that happen? Actually, it happened because 2 and 11 are relatively prime. Their GCD is 1. And according to the theory the proposition we just looked at, and we didn't really prove it, but we looked at it, this should have solutions for all B. Well, what about if let's change our colors, and we'll skip 3. 1, 2, this would be 3. 3. 3. 3. Um, one thing I noticed is that I'm now leaving from the position 1 over from the top of the clock. So I should end up 1 over from where I landed when I came from the top of the clock. I sort of can recognize where my landing point is going to be. And here I'm leaving from a position 1 before the top of the clock, so I should land 1 before where the top of the clock's line landed. Did that make any sense? I'm feeling like I babbled. I'm sorry. At the worst case scenario, you can start counting by threes again. Oh, we came back to the beginning. That's another cool looking star, more towards the center. Let's keep rolling like this. I guess the next one I want to do is skipping over 4 at a time. But look at the red star. Do you notice that there's a star point at every clock position? Every one of the 11 points of the modular arithmetic clock we're building. If I go over 4, it's to here. That's 3, so 1 more is 4. 3, 1 more is 4. Oh, that's kind of cool. I can follow the red lines and then just go 1 more step. You see how that gets me 4? The red lines are 3s, and there's 1 leaving every point. So add 1 to 3 and you get 4. How many times do I have to go around here? Oh, not too many more. There's the close-up. I'll come back to the beginning. That green star is pretty cool looking. What does 5 look like? Nice. I can use that same strategy I just was playing with. What's a good color? Sky blue, I guess. Cyan, it's called. Start here, follow the green line, then +1. Follow the green line, then +1. Green, then +1. Where's the green? There it is. +1. Green, +1. Where's that green? +1 to here. Oh man, when am I going to be done? Well, I'm going to have to hit every point, so it's actually going to take me 11 steps. I know that in advance, don't I? Oh, I thought I was closing up, but not yet. Here it is. And that's all the possible stars on this prime clock, because if I went any farther, I would just trace one of these same things, but in reverse. Really? Like, if I tried to do, let's put a color on it, it's purple. If I tried to go 1 more than what the cyan curve was, what was that? 1, 2, 3, 4, 5. If I tried to go 6, I would go to here. And then I would find that I'd end up, well, the line that I would draw, let's go ahead and do it. I'm going to go with 6, which means follow the cyan curve and add 1 more. Make it here. But do you see that I just landed on top of another cyan line? If I then went cyan and 6, I went here, and I just landed on top of another cyan line. Cyan, 1 more, I go here, and again, I'm just tracing the same lines. So I'm just going to get, I'm going to cancel because I'm just going to get another copy of the cyan star. In fact, what I'm getting is the cyan star traced in reverse of the way we did it. Why is that? Because multiplying by 5 and multiplying by 6 in congruence arithmetic are very closely related. You see, how to say this? These are negatives of each other. That's the best way to say it. 5 plus 6 gives you 11. So if you have two numbers and they add up to 0, because 11 is the clock size, so 11 counts as 0, then they're negatives. So multiplying by 5 and multiplying by -5 just get me the same star, but in reverse order. It's kind of cool. All right, so the real point here is that every single possible star is in front of us, and they all hit all 11 points of the clock. And that means we never have these types of congruences that have no solutions. All solutions have all congruences have solutions. That works anytime you have a prime clock size. That's going to be something that we will actually find useful, that we can always solve ax equals b, or ax is congruent to b modulo a prime. So now I really will go to the board and we'll look at some of that. So the thing I want to do here on the board is a little bit of a deviation from what Dr. Chrisman does in the book, but I think you'll find it useful. What I want to show you are a relatively quick way to find something that are known as modular inverses. So that is, given some number A, find a number B such that too many humps on that M. Find a number B such that A times B is congruent to 1. I'm feeling like the A here and the A here may get confused, so here, let's just try to change it up. Use a capital A and a capital B. But the idea is that the product of those two things is congruent to 1, mod whatever our modulus is. And in the particular case where n is p, you can always do this. If it's not a prime number, then you may be able to do it for some numbers, but not for others. But if you've got a prime number there, you're always able to do this. That's somewhat surprising, I think. But it has to do with those stars that I was just drawing, that every point on the graph, every point on the clock has a star point on it. Well, if you can do this, one way to think of B here is it's 1 over A. It's the reciprocal of A, because obviously we don't have fractions in modular arithmetic, but I suppose what I'm trying to say is that B acts like 1 over A, because 1 over A times A certainly gives you 1. So for instance, let's look at mod 7 and see if we can find 1/2. Okay, I should probably say it a little cleaner, because saying 1/2, obviously that's wrong. I mean, technically it's not right, but how about if I say 2 to the minus 1 power? That doesn't seem bad, does it? What is 2's inverse? 2 to the minus 1 mod 7. Well, this is pretty quick, because what you do is you basically write down all the things that are 1 mod 7. In other words, you write down this congruence class. And that consists of, 1 itself, and then 7 and 1 is 8, and 14 and 1 would be 15, and it's infinitely long. But what I'm looking for is one of these numbers that has a 2 in it, that is divisible by 2. Do you see it there? 8. So go ahead and divide it. 8 over 2 gives me 4. And I'm claiming that's the thing that acts as an inverse for 2. Because, after all, 2 times 4 gives me 8. Cool? No? Yeah. We're going to need this list of the elements of the congruence class of 1, so let me maybe do a bit more of it. Next one will be 22. Then, what am I doing? Add 7, 29. And add another 7, 36. That's pretty cool. So, yeah, let's keep track of what we have discovered so far. What I've done is I want to keep track of x and x inverse mod 7. And so 2 I found had 4 as its inverse. I guess the next thing I should do is figure out what 3's inverse is. Really easy to do with this list in mind. You just go down a list and look for something that's divisible by 3. And the other factor is the inverse. What's the inverse of 1? Because I don't have 1 yet. Oh, well, that's silly. 1 times 1 isn't. Yeah. 1's inverse is always itself. Didn't really need to do that. What's left? 1, 2, 3, 4, 5. Oh, 6. What's the inverse of 6? That's why I needed to go. I left out a lot of commas, didn't I? That's why I needed to go that far. 6 goes into this one. It doesn't divide any of these other ones, but it goes into this one 6 times. 6 is its own inverse also, just like 1 was. And this is actually kind of cool because what we're saying here is, well, 6 is 1 before the end of our clock. It's 1 smaller than the modulus. So 6 is congruent to -1. Does it surprise you that -1 is its own inverse? Not so much, because -1 times -1 is certainly 1. Yeah. So if you have inverses like this around, you can solve congruences. It's really, really pretty nice. Suppose I had, for instance, well, let's do a 1 mod 7. Suppose I wanted to know that 3 times x is congruent to 2 in mod 7 arithmetic. I want to solve for x. What I'm going to do is multiply by 3's inverse, by 5, on both sides of this congruence. So I have 5 times 3 times x is congruent to 5 times 2, all done mod 7. Well, that's 15, but 15 mod 7 is 1, so that's just gone. That was kind of the point of multiplying by 5. And 5 times 2 is 10, but in mod 7, that's really 3. So we've got x congruent to 3 mod 7. And that's real easy to check back in the original thing. 3 times 3 is 9, and 9 is congruent to 2 mod 7. It is. 7 plus 2 is 9. All right. So there's 2 techniques in the general situation where you don't necessarily have a prime number as the modulus that we're going to look at. What in the book are called cancellation technique 1 and cancellation technique 2. So cancellation technique 1. Looks like this. If you have everything in a congruence is a multiple of some number, I'm using D for that number, and I mean everything, even the modulus. If you have that situation, and I mean these things are actually congruent, then, well, actually it's if and only if, you could divide everybody by D and get A is congruent to B mod N. Should we do an example just to see this? Well, before I do an example, let me just point out the way we're normally going to do this is if we'll notice some common factor between all the things and we'll divide it out, and now we're dealing with something smaller. That's good. So once you can you're dealing with something smaller, you can, well, maybe do what I just did. If we've made this smaller and it turned out n is prime, we can find a modular inverse and do it that way. But there's another cancellation technique we'll look at in a second. Yeah, let's do an example of this. Suppose I had 15 is congruent to 36 mod 21. And that is true, in fact, because 21 plus 15 gives me 36. So 36 is 15 greater than a multiple of 21. But what this cancellation part 1 says is, notice how everybody's divisible by 3? Divide them then. So you get 5 is congruent to 12 mod 7. Is that correct? Sure it is. You can quickly see it because these differ by 7. So, not just a multiple. Ordinarily, we have to worry about the difference being a multiple of 7, but these are literally, they differ by 7. Okay. Similarly, suppose I took something like 3 is congruent to, I should make a line or something, I'm doing something new. 3 is congruent to 10 mod 7. And I just multiply everything in sight by 2. That becomes 6 is congruent to 20 mod 14. That works. 20 minus 6 is 14, so yeah, that works. So I can both divide everything in sight by any common number that's in there, or I can multiply everything in sight by some common number and get a new true congruence. Well, let's prove this. I think we should prove this. The statement is going to be, well, yeah, let's just say it. Proof. I'm going to actually do a bunch of if and only if steps. So we'll start with the top. Okay. So we'll actually, you know what? Now I'm going to try to write it in prose. I was just thinking maybe I should do it as a 2-column proof, but I think it's better to work in prose now. So given that AD is congruent to BD mod ND, we have to ask ourselves, what does that mean? It follows well, it follows that the difference, AD minus BD, is divisible, or rather, is a multiple of ND. How should we say this better? ND divides AD minus BD. Sorry. That wasn't an absolute value bar, that was a divide sign, so I need a parenthesis there. There we go. So, well, you know, I can factor a D out of this, and it just looks like ND divides A minus B times D. And I guess that's okay. Can you see that I could just cancel those D's? That's actually often a proof that you've done in a Math 250 course. Maybe we can't see that, so let me fill in sort of a mini version of that argument. What does it mean for one number to divide into another? Well, it means there is an integer that is the factor. That is, there is a k in the integers, where nd times k gives me a minus b times d. Now this is no longer, I've translated the thing that involved the division sign, the divisibility sign, into something that's just a plain equation. Is it now okay to cancel a d off of both sides? Sure, d is, the smallest d could be as 1. It's certainly not 0. So we can do that. And you get nk is equal to a minus b. But you know what that is? Yeah, that's the definition that n divides into a minus b. And that is how we know that a is congruent to b mod n. So you'll notice that I started with the version of this where there's a d in each part, and I ended with the one where the d's are missing. We should also probably go through the reasoning that goes the other direction, that if you start with this, can you end with that? But it's actually the same reasoning, so I'll just say the converse is similar. And if you'd like, that's actually a great exercise if you're a little worried about your proofwriting skills. Try to follow these steps in reverse to turn a being congruent to b mod n into ad is congruent to bd mod nd. The other canceling idea, actually I'm going to think of it as a multiplying by something idea, but you do in fact use it to make the problem simpler, smaller. So this is canceling type 2. It has a little bit of well, it's a very similar feel to it, except with one distinction. It's that A being congruent to B mod n if and only if AD congruent to BD mod n. The difference between here, this, and the last statement is just right there. That's the difference. Before, there was a D in each one of these terms. Now, there's no D here. Difference. So just notice that the modulus isn't changing in this one. Both congruences are done mod n, but we have multiplied by D. Now, there's a proviso, or there's a couple of things you need to check for. Would it be okay to write to have D be 0? Well, if D were 0, I could take something that wasn't true, and by multiplying both sides by 0, I'd create something that was true. So that would not preserve the truth. I could, for instance, if I had 2 is congruent to 5 mod 11, which is not true, right? But if I had multiplied by 0, I'd have 0 times 2 is congruent to 0 times 5 mod 11. So this guy is false, but this guy's perfectly fine. 0 is congruent to 0. You don't want to have an algebraic operation that's going to take a false thing and create a true thing. So that's just to convince you that D should not be 0. But there's one other thing that we need. Really what we need is for D to have a modular inverse. So the hypotheses for all of this are these two things. D is not 0, And D has no factors in common with N. That is, the GCD of D and N is 1. But if that's the case, then you can multiply by D. And so multiplying by D may seem like a bad idea because it's making it bigger. But remember, we're working mod something. So sometimes you multiply something by a number and it gets bigger, but it ends up getting closer to a multiple of n. So when you do the reduction mod n, it gets smaller again. All right, so from here, I want to just run you through one of the examples that's in the textbook. So we'll go back to the screencast. Right, we're back on the textbook here. Here's a thing. He presents it just as a fact, some strategies that you can use. So this is our cancellation 1 rule. If a, b, and n are all divisible by a common divisor, just divide that divisor out of everything. It's important to remember, though, that your final solution has to be returned to the mod n scenario. So if you were working mod 33 and you divide by 3, now you'll be working mod 11. That's fine. Get an answer mod 11, but then convert back and find an answer mod 33 in the end. The other thing is if A and B share a common divisor, which is co-prime to the modulus, that would be the D in that cancellation 2 rule. You can cancel that out of A and B only, like it says there, only, not out of the modulus, just out of A and B. Okay, so there's a good example of this. He calls it a big example. I like this. So we're going to solve 30 times x congruent to 18 mod 33. That's weird. 33 is the modulus I just randomly picked for a second ago for illustrative purposes. All right, so you see that they all have a coefficient. They all have a common divisor. They're all divisible by 3. So you can divide that out, but don't forget, he's got it in here in italics. Keep in mind that your final solution will need to be mod 33, not mod 11. So, all right, so if we do divide everybody by 3, we've got this new congruence, 10x congruent to 6, 18 over 3, yep, mod 11. Now, I would say we're basically done, right? Because I'm looking at this from the perspective of modular inverses. And 10 mod 11 is -1. So what's its inverse? Itself. So I just multiply both sides by 10, and I get x. I know it's 100x, but 99 is a multiple of 11, so it's really just x, is equal to 60 mod 11. Well, let's follow through what Dr. Chrisman, I was stuck on the guy's first name. I couldn't think of his last name for a second. Anyway, see what he did. He would say, I think, that we'd use the cancellation strategy 2 now, because you see how both of these numbers are even, and we're working mod 11. 2 doesn't have a common factor with 11, so you can divide the 10 and the 6 by 2. And that gets you 5x congruent to 3 mod 11. So, okay, and we're going to try to replace 3 by another number that's congruent to 3 mod 11. Why would we do that? All right, let's just try to follow it along. He says, first, I could try 3 plus 11, 14. That's another thing in the congruence class of 3. And then we get 5x congruent to 14 mod 11. Oh, but we want to look at something that will allow us to use that cancellation 2 idea again. So we'll be able to divide stuff out. So 14 wasn't good because it doesn't have a factor in common with 5. If I add 2 11s to 3, I get 25. Oh, and that does. Now I've created 5x congruent to 25 mod 11, and I can divide both sides by 5. And that becomes, there it is, x is congruent to 5. That's literally the answer. We've solved for x by doing that. Oh yeah, okay, so now we've got an answer mod 11, but we're seeking an answer mod 33. Well, there are 3 things mod 33 that happen to be 5 mod 11. There'll be 5, and add 11 to that and get 16, and then I'll add 11 to that to get 27. But there they are. They've said they got the things I said they would get, and they've written a general form for it. X looks like 5 plus something times 11. And the k can be in z, but in fact, the k is going to be in 0, 1, 2. It's going to be those guys. They've even given us a little sage cell to evaluate. So, and I previously evaluated, so you see true, true, true there. This syntax is a list comprehension, which I think I skipped talking about this when it came up once before. So why don't we fill that gap right now and show you? It starts with a square brace and ends with a square brace. So that's the notation for a list. This looks a little bit like set builder notation. I've got an expression, and then I do that 4x in some set. It's like, for if I had such that x was in a range or inequality, that would be the same idea. But this notation of some formula and a formula involving x, and then 4x in some range, in this case it's just the 3 numbers, 5, 16, and 27, creates a list with this expression evaluated at these 3 places. And those are true, true, and true. That's a funny final observation. There were a couple of places where we could have just done trial and error, but x equals 1 and x equals 2 were never the ones that worked in any of those. So he says he's lazy. I think he's put a lot of work in. All right, so that's a good place to end for today. I think I should have this posted Monday evening, so you should have time to check it out before class on Tuesday, and I'll see you then.